Hey guys, just as people start joining and rolling in, I'm just going to introduce myself. My name is Reese, and I'm hosting virtual computer science office hours brought to you by Chegg. This is every Tuesday, 6:15 to 7:15 Pacific time. So if you ever have any computer science questions, make sure to join. And if you have any questions about any other subjects, there will always be a QR code in the corner of the screen that you can scan and see the schedule of office hours for any of your other subjects. Um, but as people come in, I'm just going to go over what today's topics are. I'm going to start off with a review of binary search trees and then go into some red-black trees, and then talk about big O notation time complexity. And then if there's extra time, I'm gonna go over some mux logic gates. But as always, if you guys have any questions about anything else computer science related, just let me know. And if things like I bring up things that you're not familiar with, make sure to drop that in the chat. These are topics that encompass first year, second year computer science students. So if you're not quite there yet, we can go over other things. This is really interactive, like a normal office hour. So if you guys have questions that I'm not covering, just make sure to drop those and we can switch gears a little bit and cover what you want to be covered. So I'm just gonna get started just as people start to come in. And I'm gonna start off with a binary search tree. So we're going to insert the following keys or nodes into an empty binary search tree. So the first one in a search tree is always going to be the root. So 40 is going to be the root. I'll draw that. 40. And then 20 is less than 40. So the left side is less than, and the right side is greater than. Okay. So on the left side, we're going to insert node 20, and then 50 gets inserted. So I'm going to draw that now. Oh no, that's a square. Sometimes GoodNotes does not know what I'm trying to draw, but really that's probably my bad. Okay, and then 10 gets inserted, and 10 is less than 20 and less than 40, so 10's the left child of 20. And then 30 is less than 40, but greater than 30. So I'll put that there. And 45 is greater than 40, but less than 50. So we make it the left child of 50. Made it a square again. Okay, so that's the resulting binary search tree of those nodes. And I'm gonna hit you pause right now just as like more people start to come in and go over again what we're doing. These are computer science office hours hosted by Chegg. My name is Reese, and any questions that you have, this is just like a normal office hour, just virtually. So anything computer science related that you're covering in your classes that you want a little bit of review, I'm just doing practice problems for anything like a computer science minor would do, anyone like just starting computer science in their first or second years of college, anyone who's a self-taught programmer, like all of these things could be helpful. So just anything that you want to do, practice problems on that you guys have questions on, just make sure to let me know and we can go over that. And today, if you didn't catch that, these are the topics that we're covering. So if you're not interested in those, just make sure to drop that in the chat if you want me to cover something else, because this is super flexible. And if you have other subjects that you want to cover, just make sure to scan that QR code and you can see the schedule of hours. But if no one else has any other topics you want me to cover, then I'm just going to move on to the next practice problem. Okay. So here we're given the in-order traversal of a binary search tree. And what an in-order traversal is, if you guys remember from your classes, is it goes down the left side of the tree, then it hits the root or the node, and it prints that, and then it traverses the right side of the tree. Okay, so if 30 is printed first, wait, that doesn't make sense. That wouldn't be an in-order traversal. I'm so sorry. I messed up on that question. This is not an in-order traversal. This is a pre-order traversal. So this is a pre-order traversal. But an in-order traversal would have been 10, 20, 30, 40, and 50. So in order means that the first number is going to be the leftmost node of the tree, which will be the smallest number. So 10, which will go here. And then the parent of 10 will be 20. And then there are a lot of different trees that could give the same in order traversal, but I'm just going to draw one of them. So the next node, and that could be the parent of 20, but I'm going to draw it as the right child of 20. 40, I'm going to have as the parent of 20. And I'm going to put 50 as the child of 40. So that's one way to draw the in order traversal of 10, 20, 30, 40, and 50. And that's just some quick review of those things. So if you want me to go in depth on binary search trees or traversals, just drop that in the chat. Actually, I'm gonna X out this and put in the real traversal. Oh no. Okay, there we go. So, and then if you guys want to review anything that I go over, these videos will always be recorded on the live section of Chug's YouTube channel. So you can go back and walk through what I did. And if you want to follow along, that would be great and try these problems for yourself while I also do that. But getting into big O time complexity, we're going to talk about binary search trees and the time complexity and big O notation. And big O notation, if you're not familiar with it, is something like you just put an O and then you put like some function of the number of elements. So some function of n. So like, oh no, my cursor sometimes loves to get on the page and then it makes a big line. So like O of n squared would mean that the number of instructions would be, or the number of operations is n squared, the number of elements. And then an exponential big O time complexity is 2 to the n, where as the number of elements increases, the complexity goes up exponentially. So those are really terrible algorithms. If your algorithm is exponential time complexity, then that is really bad and you need to rewrite it. So we're going to talk about the time complexity of binary search trees. And if you're just joining now, my name is Reese, and these are computer science virtual office hours hosted by Chegg. We're working on binary search trees, big O time complexity, and red-black trees. And if you have any other topics in computer science you want to go over, just make sure to drop those in the chat, and we can go over that. So the worst case height of a binary search tree will be n. Oh, I'm so sorry. It always does that. I need to be better about moving my cursor out of there. Where were we? Right here. Okay. So the height, worst case, will be n. So n elements. Because in a search tree, right, if we keep getting elements that are less than the root and less than the child and so on, we could have a tree that ends up looking like this by the end. Or conversely, if we have a root here and then a child bigger than the root, and then bigger than that, and bigger than that, we end up with a tree that is only getting bigger in only one line. So then the height of the tree will end up being n elements, worst case. Best case would be log of n. Log n. And that's because ideally a well-balanced tree will be about exponentially log 2n the height of log 2n the number of elements. So like this tree is 7 elements and a height of 3. So as there are more elements, the height doesn't change by as many elements as there are. Like here, if there's 1, 2, 3, 4, 5, 6, 7, 8, 15 elements, there's only a height of 4. So that's why the complexity is log n of the height. All right. The time complexity for searching a tree, worst case, would be n, because worst case, the height of this tree is n, so you might have to search the entire tree to find the element you're looking for. Best case would be, oh, I have to put these in. We're doing big O notation now. So O of n, and the best case would be O of 1, and that would be if the element is or if the element you're looking for is the root, and that would just be one operation. Insertion, worst case would be big O of n. And same thing, if you have to insert all the way at the bottom and there are n elements of the height. And best case, again, is constant time complexity, where you just insert it and it's the first element inserted. And then same thing with deletion. The worst case is n elements, and the best case is constant. So I got a question about how to convert a sorted array to a binary search tree, and that's a really good question. So in a normal binary search tree, right, if you have a sorted array, make a new page. And just to pause right here, if people are just joining, these are computer science office hours, and my name is Reese, and this is brought to you by Chegg. So we're just going over any computer science questions you're facing in your classes that are really difficult. We're doing some practice problems, but if these topics of computer science are interesting to you, if you want to cover other computer science questions, just make sure to drop those in the chat and we can work on those. So this is how to convert a sorted array into a binary search tree. So a sorted array will have n elements. So it'll be an array of n, an integer array. But it'll be sorted, right? So that's actually not good for a binary search tree, because if it's sorted, um, like say it was all integers 0 to n, right? If we insert the integer 0 at the top in just like element to the greatest element, and we go 0 here, 1 here, 2 here, and so on all the way to n, we have a really unbalanced search tree. So we don't want to take that route when converting a sorted array into a binary search tree. What we would want to do instead is use a data structure like a red-black tree, which is self-balancing, or if we know that it's already sorted, we would probably want to go from the middle and make the root the middle, because if we used an algorithm where we took the n over 2 element as the root, and we had that be the root, then ideally we would want the 0 element to be here and the n element to be at the bottom of the tree. And then it would be something like this, where we would have the n over 4th element here, the 3n over 4, where it's perfectly balanced, so that it's sort of like a binary search where we would take the elements and put them in their perfect order so that it was balanced. Like if it was the number 8, then if n, we would have here, 0 here, or sorry, 4 there. Where? Um, wait, n over 4, sorry, over 4 is 2. 2 here, 6 here. I have this, and then this child would be 7. And this child would be 0, and we'd have 1 here. And then we would also be able to have, oh, that's wrong, sorry. We would have here be 5, and here be 7. And here would be 3, and it would be that. And that way you can see that it's like pretty balanced. It's not perfect, but so it's kind of difficult with A, but there are algorithms that work. Okay, trees, which are super helpful and would be helpful with with balanced trees because they are self-balancing. So when you start adding nodes and you start adding numbers, it will balance out so that the height of the tree will always be the most optimal. So just pausing here. We're about a quarter-ish way through the session. So if people are just joining now, these are computer science office hours hosted by Chag, and my name is Reese. We're talking about red-black trees right now and big O time complexity. So if you're facing any of these subjects in your classes, just follow along. If you want to go back and see why I did anything, just make sure to look at Cheg's live YouTube, and all these videos are recorded and posted there. And if you want me to cover something different, computer science related, just make sure to drop that in the chat as well, and we can cover that. Okay, so given the following numbers, we're gonna insert them into a red-black tree. So starting with the first element in a red-black tree will always be black because the root of a red-black tree has to be black. And then we'll insert 15. So, shoot, sorry. Sometimes my hand gets in the way too. Okay. So 15 is less than 20, so we insert it like a normal binary search tree. We insert it here. But it can't be black, right? Because then it would be imbalanced, like the number of nodes from the root to the leaves has to be the same number of black ones. So this has to be red. Otherwise, this would be 2 black nodes to this side and 1 black node to that side. We have 15 be a red node, and then we insert 25, and same thing, we'll insert 25 as a red node. Okay. And also the other thing, if you remember in your classes, is that these little null nodes, like that don't really exist, are black. So just like to keep that in mind of what you're looking for when you traverse a tree. So like to get to this node, it travels through 1 black node each time. And that's this one. So we're just gonna keep track of that as we go to help. Okay, so we're gonna insert the number 10. So 10 is less than 20 and it's less than 15. So that's gonna go here. But the problem with that is that if we have all our null nodes here, right, this takes one black node, this is two black nodes, and these are one black node, and they all have to be the same. So that's not gonna work. So what we're gonna do is we change the colors of 25 and 15 to be black to compensate for that. Okay. And 10 will now be a red node. 25, okay. So now this leaf node has two, these both have two, and these both travel through two black nodes from root to leaf node. Okay, then we'll insert the node 5, and that's gonna go here. But this time we can't just change a color to compensate for this, because red nodes cannot have red children. So 5 can't just be a red node, and if 10 is a black node, then it's gonna be imbalanced, and it's the same problem we had before. So what we have to do is rotate this to the right. So now 15 will be our root, and here is 10, here's 20, and 5 and 25 are gonna be red nodes. So that way, if we count it up again, the path from root to null node will be 2 for all of the null nodes. And our tree is perfectly balanced. As you can see, like, the height of it is symmetrical on both sides. Okay, then we're gonna insert 30. So 30 will go here. And same thing, so again, it's a little bit imbalanced, right? So to compensate for that, we have to rotate this node and rotate this little tree to the left. And when you write your algorithms for this, all of this happens automatically. Like, you write algorithms to take all of this into account and self-balance the tree. So that and the reason we do all this work is so that the time complexity of all those operations we talked about is a lot less than big O of n. So this will be 20 and this will be 30. Okay, so you can see again that the height of the tree is as low as we can possibly get it, which is awesome. We love that. Okay, so here's one more practice problem before we get into time complexity again. And before we dive into this, I'm just gonna stop here again. So if people are just rolling in, or if people have any other questions or anything they want me to cover that's not trees or any other data structures you want me to cover, I can do that. So my name's Reese, and if you're just joining, and these are computer science office hours hosted by Chegg, and just, let me know in the chat how you're doing with your concepts, if you have any questions about anything I'm doing. If I make a mistake, I make mistakes all the time, so you have to make sure that I don't make a mistake. And yeah, if you want me to do something different, just also drop that in the chat. Okay, so I'm just gonna draw this really fast because I like it like that, but oh, that's supposed to be black, I'm sorry. See, sometimes I write these wrong. Okay, 30, 70, and 20. There we go. Okay, so now we're gonna insert the node 25. So if we insert it just like a normal tree, it will be here. And that's not gonna work because if it's red, its parent cannot be red, and if it's black, then that's too many black nodes for some of the elements and too little for some of the others. So we have to figure out how we're gonna balance it. And what we're gonna do for this section of the tree is we're just gonna rotate it to the right, I believe. That's right. We're gonna rotate it to the right and then rotate it to the left. So we're gonna rotate 25 and 20, and then we're gonna rotate 30 and 25. So if I draw this out, I'll have 50, 70 here. And then because we rotated it twice, we're gonna root, and we'll have 20 as its left child and 30 as its right child. Okay. So that way we don't have a tree that's extending down and down and down really far on like the left side of the tree or the right side of the tree. We have a perfectly balanced tree. And just going back to my problem and why this was wrong, and I had to change this, it's because 30 was a red node and 20 was its red child. And remember, a property of red-black trees is that red nodes can never have red children. So this would not be a valid tree, which is why I had to fix it and make this a black node instead. Okay, now moving on to why red-black trees are so awesome is the big O time complexity of them. So what is the height of the tree? And worst case and best case, the height of the tree is always gonna be big O log n. And that's because, as we saw before, right? We saw that the tree is always self-balancing. Like the height of the tree is always going to be constant. Okay, and then searching, worst case is going to be log self-balancing. Just like the binary search tree, the worst case was big O of n. This one's log n, which is a huge improvement, especially when there gets more and more and more elements. We do not want to search the entire tree for an element. And then best case is just going to be O of 1, just constant, and that's the only case that that happens is when the element is the root. So that's really rare. You never want to think about things in best case time complexity because that really doesn't happen. You want to have the worst case time complexity be as low as you can. So insertion, going to be the same thing. O log n, best case constant if it's the first node in the tree, and then deletion is same thing. Okay, awesome. So actually, is that true? Is the insertion? Let me check. It's true. Because sometimes insertion takes a little bit longer, but I think it's O log n. But if you know differently, make sure to drop that in the chat. But it's just because there's sometimes more operations that you have to do, as we saw before with self-balancing the tree. But I think those operations are constant. So we have log n of getting to the bottom of the tree, and then at most we'll have like a couple moving ones, but log n plus 2 is still log n. Okay, and then moving on to big O time complexity. If you guys are just joining and interested in big O time complexity, we're going over some practice problems for computer science office hours brought to you by Chegg. And what I think is hard about big O time complexity is it's not always super intuitive and it's sometimes really hard to follow. So I always like to do these practice problems just to make sure that like I understand like how programs algorithms execute and make sure that my algorithms are as efficient as I can get them to be. Okay, so a linear search on an array. The worst time complexity of that is going to be big O of n, right? Because we have our array, and worst case, we have to look through all of the elements to find the element we're looking for. And then a binary search on the array, a binary search on the sorted array is actually going to be big O log n. And that's why sorting algorithms are super awesome, and is because if you can get your array sorted, then you can use a binary search, and kind of like a binary search tree, right? You know which side of the tree it's gonna be on. You can start in the middle, and then if the number is less than that, you can go to the left. If it's greater than that, and go to the right, and it's a lot easier to get through the tree that way, or get through the array. Okay, and then inserting at the end of the array or of an array. At the end of an array, that's just gonna take constant time because you know where the end of the array is. You can just insert right there. It's super easy. So those are your big O time complexities. And then I got a question from TikTok of how do rotations work, and that's a really good question. So for all your search trees where you're trying to um, self-balance them, all the trees that are self-balancing, right? Um, they all have to have rotations so that they are balanced, right? So how rotations work is I'll do a new example. As if I have this tree, right? Like that. Um, and then this one is this child. Okay. And it has arbitrary numbers, but I'll give it like 50, 60, 40, 30, and all right. So this tree isn't balanced, right? So if we want to balance it, we have to rotate 30 this side of the tree like that. So rotate 30 and 40. And what happens is we move 35 to be the root when we do that. And then we make 40 its right child. Like a left rotation works, immediately becomes the root, right? It's that 35 becomes the root because 30 is the left child. So 30 is the smallest number, so it can't be the root, right? If 30 was the root, it would end up like this. So actually, I'm sorry, that actually is what happened. It goes left like this, and then it does another rotation right, where 35 ends up being the root. So one rotation gets the tree like this, and I'll just draw that out. So 50, 60, 30, 35, 40, and then another rotation will result in the tree being balanced, and it'll look like this. So 35 is now the root, and 30 and 40 are its children. And when you're actually writing code for this, right, it gets a little bit more complex, but when you're rotating it to the left, you check, if it has any left children, and this one doesn't, so we don't have to worry about that, but the right child of 30 will become the parent of 40. So we plop 40 down there, and you have to consider, like, everyone's parents and children and how to handle that in writing the algorithm. Alright, so back to big O time complexity. Tracing this code, we're just gonna trace this code and figure out how many operations it takes. So print I will run n times, right? Because this for loop runs from 0 to n minus 1, and then j will run this loop will run 2n times from 0 to 2n minus 1. So our final time complexity is big O n plus 2n, which is 3n. But the reason we use big O notation is we don't care about like constants and scalars. We just care about the factor of n. So that is the same thing as big O of n. Okay. And we're a little bit more than halfway through the session. So it looks like we're gonna end up having some time for some mux questions. So if anyone wants me to have some extra questions that are different from those, just make sure to drop those in the chat. If you have any questions about big O time complexity or any search trees or data structures that you want me to go into some more, just let me know. And if not, just follow along with what I'm still doing. Okay. So the following code, it's gonna go it's a recursive function, right? And I covered recursive functions a few weeks ago, and recursive functions are hard because they're deceivingly simple, right? The function calls itself and calls itself and calls itself. But I'm gonna trace this one with a really quick example. So if we call like m of 3, zoom in a little. So if I say in my main function, I want to call m with the parameter of 3. So if n is less than or equal to 1, then we'll return 1, but it's not. So then we return m of 2 plus m of 2. So it calls this twice. So m of 2 will run, but m with the parameter of 2 will run twice. So this does the same thing. M1 m1 returns m1 plus m1, but that means m1 gets called 4 times. And that finally returns. These will all return 1, and it will stop. But that means with the parameter of 3, so n equals 3, all of these functions, there was a total of 7 functions running. 7 functions running. So that means that this is an exponential function. An exponential time complexity function, and that's terrible. We never, ever, ever, ever want to have an exponential function. So the time complexity of this is going to be 2 to the n, which is terrible. But maybe there's a way we can fix the code just a little bit to maybe have it be linear instead of exponential. And my thoughts about it, right, is why are we calling the same function twice when we're returning it, right? We're having computation be done doubly as much or exponentially as much as we need to. So I would rewrite this as the definition of m with the parameter n, and we'll have our base case, which we need to have. And then I'm just going to define a variable like a equals m n minus 1, and then I'm going to return a plus a, or 2 times a. And that cut our time from big O of 2 to the n to just O of n, right? Because the function's only called once instead of being called twice, then 4 times, then 8 times, then 16 times. And that's like, we only needed to call it once because it's the same function. And then we were able to duplicate that. So that's how, like, in your code, you can start optimizing it to make a lot better time complexity. And that's something that, like, people in your field will value a lot, is reducing the time complexity of algorithms. Like, that makes you stand out from the crowd. Okay, so that's it for time complexity. If you guys have any other questions about time complexity, just drop those in the chat and let me know. If you guys have any questions about data structures, also let me know. But otherwise, I'm just going to move into logic gates a little bit and just working on some muxes. So in our last 20 minutes, if you're just rolling in, these are computer science office hours brought to you by Chegg. My name is Reese, and we just covered some trees, binary search trees, red-black trees, and big O time complexity, and why, like, red-black trees are so much better than binary search trees. So if you're interested in that, this video will always be uploaded to Chegg on their YouTube channel under live videos if you want to review that, but otherwise just follow along if you want to review some problems about muxes. Okay, so I'm just going to open up a new page and start off with some problems. So I'm going to draw a mux with some inputs and outputs, and then we're just going to draw a truth table. So let me zoom in. Okay, that's okay. So here's our mux, and it's going to be a 4 input to 1 output mux. Need this to be bigger. So here's my little mux trapezoid, and then we're going to have a selector 1 and a selector 0, and then I'll have I4, or no, I3, input 3, input 2, input 1, and input 0. Okay, and all of this is going to be output to Y. So I0 will be 0, I1 will be 1, I2 will be 1, and I3 will be 0. So now we're going to write a truth table for the selection lines and Y, given these numbers. Okay, so we have 2 bits of input and 1 bit of output. S1, S0, and Y. All right, so if these are both 0, then I0 will be chosen, input 0, and then Y will be 0. If S0 is 1, so the number is 1, then I1 will be chosen, and Y will be 1. I'm going to put in parentheses the input it's choosing. Then I. I'm going to make these I's, because they kind of look like 1s, and that's very confusing. So this is I1, and then 1, 0 will be input 2, which is a 1. And then if they're both ones, that'll be input 3, which is 0. Okay, so that's our truth table. And I recognize this truth table, and I hope you guys do too. So this is the same as an exclusive OR. So S1 exclusive OR S0 equals Y. And this is the same thing as writing this. That's an exclusive OR, given our mux. So that's how you convert like a given mux with some inputs and outputs into a truth table and then an equation. All right, and then moving on to another problem. I'm gonna write down an equation, and then we're gonna try and create a mux out of it. So our function AB is gonna equal A times B, or plus, not A times B. Okay, so the first thing I'm gonna do is make a truth table. Truth tables are awesome because it just helps you digest the data a lot better, and then you don't get confused. And when I don't make one, I get confused a lot easier because it's just zeros and ones, so that's really easy to mix up. All right, so if these are both 0, then f is going to be 0. If a is 0 and b is 1, f will be 1. If a is 1, b is 0, f will be 0. And if they're both 1, f will be 1. Okay. And last week, if you guys were there, I worked on some Boolean algebra simplification. So we're also going to do that, but first we're going to draw the mux. So there's a bunch of ways we can draw this, but I'm going to draw it as A being connected to the selection. So here's my mux. There we go. And our selector is going to be A. Oh no, I drew it backwards. Super my bad. Okay. So here's that. And it's going to output F. And then we have to decide what our selectors are going to be. So this is input 0 and this is input 1. And we want to decide the selectors so that this truth table will always work. So what I do is I look and I see, okay, if A is 0, then F is B. And if A is 1, then we can see what it is. And turns out F is still B. So we don't need to really have this mux at all, right? Because it doesn't change. Because both selectors are going to choose B. So that's like a case where you can decide that a mux is a bad logic gate to use for that. But I'll give you a problem where maybe a mux is like a little bit of a better gate to use. And as far as Boolean algebra goes, I showed last time how if we take B out of this equation, right, by distributive property, we get that. And A or not A will always be true, no matter what. Like A can be 0 or A can be 1, but it can't be anything else. So that's the same thing as B times 1, which is just B, which is why we got that answer of both of them being B, because it doesn't matter what A is, the answer will always be B. So I'm going to do a new equation where F is going to be not A and B or A. All right, so we're going to do the same thing. We're going to draw the truth table. This is A, this is B, and this is F. So if they're both 0, that's F will be 0. If B is 1, F will be 1. If it's this, F will be 1, and lastly, F will be 1. Okay, so in drawing our mux, right, we're gonna connect A to the selector again. So I'm gonna draw this again. I'll draw it the right way this time. All right, so A is here, and then we need a 0 input and a 1 input. Okay, so when A is 0, if A is 0, then we can see what F is. And here we can see that F is equal to B, just like last time. But if A is 1, F doesn't equal B, F looks a little different. F will actually be 1. So here, I0 is going to be B, and I1 will be 1. And that gives us our multiplexer on how to translate that equation into like a truth table and then some logic gates. So I hope that made sense. If it didn't, just drop that in the chat. And as we're kind of wrapping up, I'm just gonna do a few more logic gate problems, but as you guys are getting ready to leave and stuff, just make sure to drop things in the chat that you want me to cover next week. So if you want me to do things like proofs or theory, I can create practice problems on that. I can do more digital logic. I can do combinational or sequential logic if you're taking that in any of your classes. There were also some questions about like other data structures, and I can do that as well. I can also go deeper into time complexity if you want me to do that. So yeah, just drop those in the chat and I'll make sure to have practice problems for those. And as always, if you guys want 24/7 help, just make sure to go to chegg.com. And if you guys want to go to office hours for any of their other any of your other subjects, just make sure to scan that QR code and you can see the schedule. You can see when we have those live office hours. All right. So I'm gonna have another equation, and I'm gonna draw this as a truth table and then our mux. And look at it. This one looks a lot different. So we don't see a lot of Boolean algebra equations like this where selectors are in the equation. But there's still a super valid way to represent muxes. Okay, and then, oh, I need some knots in there. Okay, so this is, and that's a knot, and then those two are knots. Okay, so this is called sum of products, and what that means is we're adding up all of the cases where y is true. And we can see that right here. And in this case, we're not necessarily doing y is true, or we are doing y is true here. Okay. So when S0 is 1 and S1 is 1 and A is 1, then Y will be 1. And when S0 is 0 and S1 is 1 and B is 1, and we don't care about any of these other things. Then y will be 1. And then if S0 is 1 and S1 is 0 and C is 1, y will be 1. And then if these are both false, then y will be 0 because this is always not true. So these show the cases of the outputs when S0 and S1 are different things. So all other cases will always be 0. We don't care what the other inputs are. If S0 and S1 are 1, but A is 0, it doesn't matter what the other inputs are because Y will be 0. So it's showing, like, based on this equation that sorry, based on this equation, what the I hope I didn't get disconnected. Based on this equation, what will the output be of the mux? Okay, so I'm just gonna draw that right here. I did it backwards again. Okay, so we'll have selector 1 and selector 0 and y. All right, so this is saying that y will be 1 when these are both false. No, this is actually 0. When these are both false, then y will always be 0. If S1 is 0 and S1 is S0 is 0 and S1 is 1, that will be this case, and then the input will be C. Input 2 will be B, and input 3 will be A. And that's because, like, this equation is describing all the cases where y is 1, right? So if A is 0 and S1 and S0 choose 3, then y will be 0 because A is 0. So it just matters what A is, what B is, what C is, and their corresponding inputs. But another way to do this, right, is to have logic gates instead. So you can do these kind of logic gates, right, and just have ands and nots. But it's actually a lot easier to use mux as the gate than it is to do, like, individual ors and ands because that's a lot more drawing than just one simple mux. Okay, so for one last problem, as we're wrapping up, I'm just gonna one more quick mux problem. And, as a quick goodbye, like, thanks so much for joining. It's wonderful to be here every week, and if you guys want to have if you want me to address more computer science questions next week, just make sure to tune in. It's at 6:15 and 7:15 every week at Pacific Standard Time. And if you have any other questions about your other subjects, scan that QR code and go to their office hours, and then go to chegg.com for 24/7 support. Okay, so one last question is I'm going to say that y equals A and B. And I'm gonna make my truth table really quick as we wrap up. And it's 0, 0, 1. And my selector is going to be B. So input 0, I'm just going to say is going to be 0. And input 1 will be A. And then you guys on your own can figure out why that's the case and do that problem on your own. And as always, these videos are always recorded, uploaded to the live section of Chegg on YouTube. So just make sure to follow Chegg on YouTube, Twitch, Instagram, and TikTok for more of the support. We have our live office hours every time during the week with that schedule, and just support on chegg.com. So thanks so much, you guys, for coming.